Our last application we're going to look at are these pumping problems, and we could pump out a fluid from some sort of tank that has a height of 8 meters. Now we still have our work formula, okay? So mass times gravity times distance y. And what we're going to do is we're going to partition the tank and the fluid into cross sections of fluid, and we're basically going to get like little areas of the fluid or little slithers of the fluid. And what we're going to do is we're going to pump each of those little slithers out. All right, so if we know the density of, so let's look at our diagram here. And let's say that we know the density of this little slither here. All right. And we know that this is going to be the distance. All right. Which is going to be our y. And we certainly can figure out what the area of that is. All right. So we would just take our area times our distance times our density times gravity. And that would tell us how much work it would take to pump this out of a height. All right. Now, we have to keep doing that though. So we have to do it for this one, and all of them actually. All right, but just illustrating. And that would work nicely if we had a static, okay, sort of like basically like a nice rectangle or like, a really easy object for us to do the computations for. But we know a lot of times the tanks are going to be curved, and that means that they're not necessarily going to have some sort of consistent or just some sort of static sort of cross sections. So what we're going to do is we're going to theoretically take an infinite number of these cross sections, and we're just going to find the areas. We're going to find the gravitational constant, the density function, and then this is going to be the height that we're going to pump that out. Okay, so h minus y sub I. So the height basically minus how far down in the tank it already is. All right, and obviously the deeper it is in the tank, the harder it is to be able to pump out. All right, so now of course we want an infinite number of those, and if we do that, if we take an infinite number, that means that the delta y sub I is going to go towards 0, and we get an integral surprise. And so what we're going to do is we're going to find the work by finding the area of one of the cross sections. So we're going to find a formula for the area. We're going to multiply it by the density, the gravitational constant, and then the height minus whatever y might be. And y is variable. Okay, so remember, as we're going up the tank, y is going to eventually get to 0. Okay, because or h minus y is going to get to 0. Okay. All right, so let's take a look at a couple examples or a number of examples of fluid force types of problems. Okay, we'll start off with something pretty easy. So we have a swimming pool, shape of a box, okay, that has a base and it measures 20 by 15 by 2.5 meters. All right, how much work is required to pump the pool when it's full? And it's going to tell us that we should use 1,000 kilograms per meter cubed for density of water and 9.8 meters per second square for acceleration due to gravity. Okay, so just thinking about this, all right, if we draw a picture, right, and ignore my not so good construction, apologies, all right, but let's just say that this is the pool, all right, and let's just say that this is going to be 15 meters, all right, not the scale, just so that way we can kind of see, and this is going to be 20 meters, and of course we know the height is 2.5 meters. A cross section, okay, would be, if I were to draw like a little area of this, okay, so this would be one of them, okay, so just think of this as the area, okay, or cross section. And of course, another one would be something like this, okay, where we have another cross section, all right. And so what we're seeing is that the cross sections are static, okay, each of those cross sections are the same size. So it's actually going to be 20. So I'm going to call A of Y, not delta Y, but A of Y in our formula is going to be 20 times 15. And if you want to throw meters in there, that's fine. But that's going to end up being 300 meters square. Okay, so that's pretty easy, right? And if we go back up to our formula, all right, so we need the area, we need the density, we need the gravity, and then the height minus y. And I think we have all those things. Okay, so if we have that the work is equal to our integral from 0 to h a of y, rho is our density, g is our gravity, h minus y dy. We know that the density is 1,000, We know that the gravity is 9.8 meters per second square. We know that the height is going to be 2.5 for this. All right, so given all of that, at this point, it's just substituting. Okay, so the work is going to be equal to 0 to 2.5. Our area is 300 meters square. The density is 1,000. The gravitational pull is going to be 9.8 meters per second square. The height is 2.5. And then y is going to be a variable because as we're pulling it up, we get closer and closer to the top. It takes less work to do so. All right. So, and just think about it. To go from the top here, that's a shorter distance than to go from here to the top of the pool. So it should take less. So this this little slither right here, the one that I'm coloring in again, okay, that should take less work than to pull the slither that's underneath of that. Right. So certainly we can multiply this out, right? And if we do so, that's going to equal, if I go to my super fancy calculator, that'll be 300 times 9.8 times 1,000, otherwise known as 2,940,000. So 2,940,000. Integral from 0 to 2.5 of 2.5 minus y dy. And this makes it really easy, right? So now we get 2,940,000. Right? 2.5y minus 1/2 y squared. 0 to 2.5. Right? And then substituting 0 in doesn't matter. So 294. All right. And then we're going to have 2.5 minus 1/2 of 2.5 squared, all right, minus 0. All right. And if we throw all of that in, all right, let me just go ahead. And we know that this is 2.5 squared, all right. And I'm going to use that trick before. This is 1 times 2.5, and this is 1/2 of 2.5 squared, all right. So really what we get is 294,000 or 2,940,000 times 1/2 of 2.5 squared. All right, so that makes it a little bit easier to be able to punch into the calculator. Just for mine, you guys have the graphing calculator, which is probably a little easier. So we're going to just take 1/2 of this, and then we're going to multiply that by 2.5 and then another 2.5. All right, so I get 9,187,500. All right, that would be in joules. Okay, probably a prime candidate for us to put into scientific notation if we chose to, just because this starts becoming pretty largesse. So if we wanted to put it in scientific notation, we have 1, 2, 3, 4, 5, 6 decimal places. 9.1875 times 10 to the 6th. If we wanted to put that in joules. So let me make sure that's okay. So we move it 1, 2, 3, 4, 5, 6, and that would be in joules. All right. All right. And let me just verify that I didn't mess anything up with that. Yep, looks good. Okay. All right. So that's just one of our problems with respect to the fluid flow. All right. And we know how to derive the fluid flow. We take the areas, the cross section of the areas, multiply it by our density, multiply it by a gravitational constant, and then our height minus y because it's variable. Okay, so we'll take a look at a couple different shapes in the next few examples. Okay, but hopefully that one wasn't too bad for everybody to understand how the fluid pumping problems work initially.